तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, I want to take a look back at what we have done and then make the final step from what we have been doing as wave theory to something more practical, which is the subject of transmission lines. So let us look at where we started. We started with statics. And we concluded that there were two equations which governed electric field. One was curl of E was equal to 0, and the other was divergence of D was equal to rho. Because curl of E was equal to 0, this allowed us to say the electric field is derived from a potential. So E was equal to minus grad phi. And we invented this concept of the displacement vector because any material has charges in it which are bound to where they are, to the atoms to which they belong, but in the presence of an electric field there is an induced polarization, and we worked it out in this course that you can show that D is equal to epsilon E, that is D is proportional to E. So the correct equation here is divergence of E is equal to rho total over epsilon naught. But by introducing the concept of induced electric field and saying that the induced electric field is proportional to the electric field itself, we could write this as divergence of E is equal to rho bound plus rho free divided by epsilon naught. And we identified this rho bound by epsilon naught, this piece, with a divergence of E induced. And so we came up with a new equation which was divergence of epsilon naught times E minus E induced was equal to rho free, and that is this equation. So this is nothing but D. So this was statics, and the final achievement of statics was the Poisson equation, which gave us that del squared phi was equal to minus rho over epsilon naught. Now there are some things that I didn't do here because they were purely mathematical in nature. One of them was that you can prove that if you have any volume V, and if on the surface of this volume on every point you specify either phi or del phi del n, then the solution inside exists and is unique. So that means that this equation is well defined and has unique solutions. So that was statics, that is electrostatics. Then we went to magnetostatics, and when we went to magnetostatics, the picture was exactly reversed. We found that we could write curl of B was equal to mu naught J, and we could write divergence of B was equal to 0. Now, I discussed with you that the magnetic field is not a new field. In fact, if you go back and look through some of my older lectures, the magnetic field is nothing more than the electric field when you apply relativity to it. So, it's actually a side effect of the electric field. Now, you take this equation and once again apply it to materials. This equation becomes mu naught J bound plus mu naught J free. And once again you can attach an implied field to this bound current, and you can say that this is equal to curl of B induced. Which allowed us to say curl of B minus B induced divided by mu naught was equal to J free. And we identified this as a new vector which we called H. So, we had 4 equations. One was curl of E was 0, divergence of D was rho, curl of H is J, divergence of B was 0. And these 4 equations took care of time independent phenomena. However, once you went to time dependent phenomena, 2 of these equations were found inadequate. So, we added extra terms. First, this curl equation turned out to have a correction to it, which was minus del B del T. And the effect of this minus del B del T could be seen because if this equation was still correct, which meant B was the curl of some other function A. Substituting it back in here, you found that E was minus grad phi, but substituting this curl back into this, you also got a minus del A del T. So, the electric field was not only due to a gradient of a potential, it was also due to a time dependence of the vector potential. Similarly, this equation was found to be unsatisfactory. You found you needed a new term which was del D del T. So, that gave us the final system of equations, and let me write them down once so that we can see them. Curl of E is equal to minus del B del T, Faraday's law. Divergence D is equal to the free charge, Gauss's law. Divergence of B is 0. There is no such thing as magnetic charge. Curl of H is equal to the free charge plus del D del T. That is what we call Maxwell's equation. D is equal to epsilon E, where epsilon is the permittivity. B is equal to mu H, where mu is the permeability. And we have one more equation which connects rho and J, which is divergence of J is equal to minus del rho del T. So, these are the equations that define the field, and there is one equation that is coming outside the system which happens to be at least as important as these, which is the force equation. The force on any charged particle is Q E plus V cross B. So, these are the system of equations that we have been looking at through this whole course. Initially we ignored the time derivatives and we did statics. Then we took the time derivatives into account. We got Faraday's law, induced EMF, motional EMF, and then finally we got waves. We have spent quite some time on waves now, and what I want to do is to make those wave solutions interesting to someone who is not going to be in communication theory, because really if you are not going to do AM and FM transmission, why should you learn about wave theory? Well, there is a good reason for that why you should learn, and it has to do with the fact that even if you do not do free space wave propagation, every electrical engineer, like it or not, is going to have to deal with transmission lines. So, what is a transmission line? Up to now we have looked at waves which travel in one dimension basically. We know that there are more complicated solutions, but we have looked only at one dimensional solutions. You have the electric field in some direction, magnetic field 90 degrees to it, and E cross H is the direction in which the wave is traveling. Now, the first thing of interest to us is that if you had a torch and you shone light from this torch, you know that the light spreads. What that means is if you are standing somewhere and you shine a torch at the wall, a spot will appear on the wall. If you shine the same torch at a faraway building, the spot will be much bigger, and if you shine it at a mountain, you won't see anything at all. So, what it means is that this beam is spreading out, and we worked this out in terms of Poynting theorem. We said that there is an inverse square law for intensity, namely volume integral of E cross H dot ds is constant, assuming that your light bulb is in one place. You are asking how spread out is my electric and magnetic field of my wave. What you have is E cross H dot ds is independent of how far away I measure it. If I measure using a surface like this, I will get one answer. If I measure using a surface like this, I will get the same answer. That is because the same wave is going through, there are no sources here. So, I should get whatever came in must leave. E cross H is power density if you like. We saw last time that it has the units of watts per meter squared. So, this power density is inversely proportional to the area of the surface, and the area of a sphere is proportional to the square of the radius. So, power density is proportional to 1 over r square. That explains a lot of things. It explains why the sun is not brighter than it is, how light spreads out. It explains a great number of things, but it is an inconvenience. Supposing I want information to travel from point A to point B without spreading out. Well, of course, I can design very good optics and make sure that the light does not diverge, and we do that. When we have point to point microwave links, our transmitters have only 1 watt of power and the links may be tens of kilometers apart. So, it is possible to have very low powered sources going through air without spreading much. However, that is not always the best approach. So, what we would prefer to do is to have cables. We would prefer to take this wave, package it into a cable and send it from point A to point B. Like we have our computer and we have a cable, an Ethernet cable, and it connects to a hub. This cable is also taking time dependent information, 100 million bits per second, from this point to this point, and the wave that is traveling through this cable is forced to stay inside the cable, and so it does not obey the inverse square law. That is, the strength of the wave at this point is not inversely proportional to the distance. It attenuates. There are losses in this cable, but otherwise if it were lossless, the amount of energy here would be equal to the amount of energy that left here. So, what we really want is the same wave that travels through space, except we want to bottle it into a pipe. We would like to look at what solutions one can have if I take a wave and I make it travel inside a metallic pipe. Unfortunately, there is bad news. Let us look at this along the axis. So, it has got some shape. This is x, this is y. So, this pipe has some cross section. Now, my electric field and magnetic field are what they are. So, let us say I have my electric field this way and my magnetic field is this way. Now, you can see that there are places where the electric field will be tangential to the wall. Now, we have already discussed that tangential electric field is always continuous. Since it is always continuous, the electric field inside the metal is also what it is at the wall, which means you have a very strong electric field inside a conducting material. Similarly, if you look at this point, your magnetic field has a normal component, and just as we showed that the tangential component of the electric field is always continuous, the normal component of a magnetic field is also always continuous. So, you find that whatever magnetic field is here is also inside the material. But you know that Ampere's law tells us that if you have an electric field, you have current. If you have a magnetic field, you have an induced electric field, and therefore you have again lots of current. So, if your current conductivity, if your sigma is extremely high, you cannot really afford to have a large electric field, which means that this kind of solution is not possible. If you try to package what is called a plane wave, the kind of wave we have been looking at, and put it into a pipe, the plane wave will be destroyed in centimeters. It will just not survive. If a plane wave is to survive, it must change. It must be a different kind of wave. It must actually vary not only in z, but it must also vary in x and in y. And how must it vary? It must vary by becoming 0 wherever the electric field tries to be tangential, and the magnetic field must become 0 wherever it is trying to be normal. There are such solutions, and the study of waves flowing through pipes, it's a very important subject. It's called waveguide theory. For instance, if you are doing radar and you have a building where you have generated your strong radio frequency signal, and you have your radar antenna, well, there will be some 100 meters or few hundred meters between the antenna and the place where you are generating the signal. So, this high frequency signal has to be taken there, and it is maybe 10 kilowatts of power that must be given to this antenna. It has to go through a pipe, and such waves that go through pipes and drive an radar antenna, these are waveguides. But as I said, the problem with waveguides, problem with waves flowing in pipes is that your electric field and your magnetic field are not the simple fields that we have looked at so far. They are more complicated fields. For instance, if you had a cross section that was rectangular, so you had x and you had y, then you could imagine that you would have an electric field that was 0 at the two ends and slowly became bigger, biggest, and became smaller. Such a solution is quite possible, and these kinds of solutions exist, and they are called transverse electric and transverse magnetic modes. You will see the names TE and TM modes. That is all it means. It means that there is variation in the x and y direction. A transverse electric mode is one which does not have any electric field in the z direction, and a transverse magnetic mode is a mode that does not have any magnetic field in the z direction. Unlike all these modes, which are quite complicated and not really of importance to low frequency applications, there is one special mode, and this special mode can travel at low frequencies, it can travel through pipes, and it looks like a plane wave, and it is that wave that I want to talk about today. Let us go back to the wave equation. So, we had del squared E minus 1 over c squared del squared E del t squared is equal to 0. Now, I am going to write this del squared as two parts. It is actually equal to the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. That is what del squared is. So, I am going to separate out these two pieces and keep this separate. So, del squared E del x squared plus del squared E del y squared plus del squared E del z squared minus 1 over c squared del squared E del t squared is equal to 0. I will just put brackets. These two equations are identical, because I have just written out the del squared, collected two terms and put the third term with the time derivative. Now, I am going to make a guess. I am saying I have a long tube. So, whatever shape I have in x, that shape remains what it is as I go down in z. So, if I cut here, I will still see the same shape, and if I go further, I will still see the same shape. So, I guess that the electric field has a dependence on x and y which is independent of how it depends on z and t. So, I write the electric field as some vector which depends on x and y alone times e to the j omega t minus kz. This is perfectly reasonable. I do this because I can see that in time and in z my structure is symmetric. If I shift in z, problem looks the same. So, I can look for sines and cosines in z. If I shift in time, the problem looks the same. So, I can look for sines and cosines in t. But I cannot shift in x and y because I have a pipe. So, that problem is more complicated. If I substitute this in here, and I will call this E perp, I can write this as del squared x y acting on E perp multiplied by e to the j omega t minus kz plus the del z squared will act on kz. So, I will get a minus k squared plus omega squared over c squared E perp e to the j omega t minus kz is equal to 0. So, all I have done is I have substituted this form into this equation. This part I do not know what it is going to do, it is just going to act on this unknown function. But this part I know what it is going to do because I know the form of the dependence on time and the dependence on z. So, I pulled it out. Let me get rid of this exponential because it is common. So, I remove it. Now, if I want to compare this problem with the plane wave problem, I need to get rid of this piece. Without this piece, this is nothing but my one dimensional wave equation. This piece is what is going to complicate my life. So, I look for solutions where this piece goes away. So, I try to find solutions where the del squared x y acting on this amplitude which depends only on x y is equal to 0. If I could find it, then the rest of it is done. This is a one dimensional wave equation. So, it is my plane wave bottled into a pipe and packaged and sent. Now, the question is, how do I solve this problem? I have gone from one problem to another, but the second problem does not look any easier than the original problem. So, I want del squared del x squared of my E perp plus del squared del y squared of E perp is equal to 0, and E perp cross the normal to the surface is equal to 0 on boundary, because the tangential component must be 0. Now, what I am going to do is I am going to look at this and say this does not depend on time at all. So, I will guess E perp is a vector is equal to minus gradient of some scalar. After all, it looks like electrostatics to me. So, why not try it? Even this looks like electrostatics. It says there is no tangential electric field. So, the wall is a equipotential. So, let me put this back into this. What do I get? I get del squared del x squared plus del squared del y squared acting on minus del phi del x, x hat, minus del phi del y, y hat is equal to 0. And in addition, phi equals constant on surfaces. Because I need tangential component to go to 0, so if phi is constant, tangential component is also 0. Now, because these are all derivatives without any coefficients, I can always commute them. I can pull this del x outside and I can put these inside. So, I can write this as x hat del x plus y hat del y acting on del squared del x squared plus del squared del y squared of phi. Because after all, second partial derivatives commute. So, it does not matter in which order I do del y del x del y del x or del x del y. The order does not matter. So, I will do this operation after I do this operation. But when you look at this equation, what does it say? It says minus gradient of del squared phi equals 0, which can be easily satisfied. It is okay if del squared phi is equal to 0. So, I am really looking for solving this problem. I am really looking for something very simple. I am saying I will guess that the electric field looks like this, some function of x y times e to the j omega t minus k z, and this function of x y is derived from a potential, and this potential satisfies Laplace's equation. Let us look for an example and see whether all of this makes sense or not. I will start with a central conductor and a metallic pipe. The outside I am going to hold at ground, inside is at some voltage V, and there is dielectric. Now, really I should not say I am holding it at a voltage V, it is going to carry a wave, which means that the voltage is not constant, voltage is a function of z. But when I look for the solution of this problem, I am looking for del squared phi is equal to 0, phi equals 0 on outer wall, phi equals V on inner wall. This is a well known problem, we have already done it. This is nothing but what we did for calculating capacitance of two cylinders. So, you can easily find a solution, and you know that there is a radially symmetric ER. This electric field ER will satisfy del squared phi equals 0. There is no tangential electric field on the outside surface, there is no tangential electric field on the inside surface. So, it satisfies all the conditions we want, and therefore, del squared xy of E perp is 0 and the boundary conditions are satisfied. What does that mean? It means that for this particular form, we are solving only this equation. Now, that means my solution is going to look like this. The electric field, which is a function of x, y, z and t, is really an ER along r direction. That ER you can work out is going to go like 1 over r. So, you can say E naught over r, e to the j omega t minus kz. what will the corresponding H look like? This will be the curl of E. So, when you look for the curl of E, it is going to take the z derivative of ER, that will be in the theta direction. H of x, y, z, t will again look like some H naught over R in the theta direction, e to the j omega t minus kz. And when you put these into the wave equation, you get this solution, which means omega is equal to plus or minus kc. Now, these are very special waves. These are not the waves that are used for taking high energy radar signals. They have quite a few nice properties. For one thing, the line that connects omega and k, the curve that connects omega and k, if you plot it, you find that it is a straight line. Now, this is very important, because if you look at what happens if I have a circuit and I have a switch, and I close the switch. When I close the switch, current will start to flow. Now, the speed with which this signal that the switch is closed goes through this circuit depends on how well the signal propagates through these wires. If the signal propagates at different velocities, at different frequencies, then what will happen is, out here in time, the signal, the switch just closed and instantly the signal came on and continued. But out here, it may very well be that the signal will look like this. That is to say, the fact that the switch closed was not a very sharp start in the current, it starts gradually. There is a rise time to the signal. And this rise time due to the signal comes because the wire is not carrying all frequencies with the same velocity. But this particular solution we have is a special solution. It does in fact carry all frequencies at the same velocity, because the velocity is nothing but omega over k, which is equal to c. So, all frequencies travel together. So, if I take the Laplace or Fourier transform of this signal, it is a spectrum. Every part of that spectrum travels together. I can take the inverse transform here and I will get back the same shape. It will not be one frequency is delayed with respect to the other, which is the main cause of these kinds of effects. So, that is one very important advantage of such waves, and these waves are called TEM waves, transverse electromagnetic waves, and they are the waves that live in what we call transmission lines. Now, in a certain sense, transmission lines have come to rule electrical engineering, no matter which branch of electrical engineering you are in. That is because the state of the art has kept progressing till, however fast or however slow your circuits are, they are pushing the limits, and the limits are always the limits of signal propagation through circuits. So, you can see this happening through the different technologies that are happening in different branches of electrical engineering. For instance, Naturally, in communications, transmission lines are required. Waveguides and transmission lines are automatically required. But if you look at, for example, a PC main motherboard. Now that doesn't look, that's not communications after all. What about it? Well, the size of the lines on a PC motherboard, a few centimeters, and the speed of the clock on the motherboard, which are hundreds of megahertz, combined together so that in fact signal delays become very crucial. So once again you find transmission lines are crucial. If you don't take proper care about delays, you don't properly understand your transmission lines, you can't design a good motherboard. What about an IC chip? Well, these distances of lines are now in tens of microns to hundreds of microns, but the speeds are much higher. Because the speeds are much higher, once again signal propagation delays are important, and you have transmission lines once again. So you come lower in frequency, and so you come to power lines. Now you are talking about 50-60 hertz, but your power lines are very long. Your power lines can be crossing a country, and once it starts approaching a large fraction of 1,000 kilometers, once again you are a transmission line. So the theory of transmission lines, and more generally the theory of waveguides, has come to dominate electrical engineering no matter which branch you are in. And it is the same theory. The theory cannot change because you are talking about power lines as opposed to communications. In all these cases, what is important is that you are able to separate the del squared of Ex and Ey and the solution along Z, which is del squared del Z squared minus 1 over C squared del squared del T squared of the behavior in T and Z. So I gave one example of this, which was the cylindrical 2-wire guide. That's what you call a BNC cable. It's also found in the TV coaxial cable, and all of those are machined to great precision so that they can carry these signals up to very high frequencies. But since we are talking about low frequency effects, we can also talk about power lines, because you can consider two wires, one of which is at one voltage and the other is at another. So you have current flowing into this and coming out of this wire. These are the return paths of this current. Then we are solving for XY electric fields. By solving this capacitance problem. It's a solvable problem. In fact, there are exact solutions available. And if you solve this problem and substitute it back into this equation, you've got the transmission line that is used by power lines. And this is nothing but the electromagnetic wave that travels through the hundreds of kilometers in which power is transmitted. So the power is actually going into the board, but electrostatic and magnetostatic fields are set up due to the charges and currents that get established on these wires. So it's an important thing to realize that transmission lines are a very unifying idea, and they are in fact, like you might say, the final step in a basic electromagnetics course. We have learnt about static fields, we have learnt about magnetostatic fields, we learnt about motional EMF, we learnt about waves. And when we went to waves, it was like we went to a new subject. But actually, now we have come all the way back. We are talking about using those waves inside circuits. We are talking about power lines carrying power. We are talking about Ethernet cables carrying signals. And those circuit elements are in fact waves again. And perhaps the most surprising part of it is, to solve for this wave, you need electrostatics. You are not using wave theory. Wave theory is the simple part. You have to do electrostatics. Now, if you are doing PC motherboard, you would have a high permittivity epsilon of maybe 10, 12, high permittivity material, dielectric, on which you have thin copper strips. The bottom part of this plate is actually fully copper. And it is connected to ground. This is what is called a two-layer board. And of course, standard PC motherboard will not be 2-layer, it will be 4-layer, 6-layer or higher. But this is the simplest way of looking at it. So what happens is, if you look at this structure and look at it from sideways, you have your dielectric, at the bottom you have copper, and this copper is grounded. At the top you have more copper. Current signals flow into this copper strip, that is, they are flowing this way, that is, into the board in this picture. When charges get built up on this strip, you get capacitance. You have to solve this problem. This problem would be the problem of having an air dielectric and an epsilon much greater than epsilon naught with copper strip in the middle. This problem corresponds to solving this. Having solved it, and actually there are some problems, I will not go into them. So it's only an imperfect solution you can make. Having solved them, you are then left with a transmission line. The transmission line carries signals along this wire at essentially the speed of light, actually half the speed of light approximately. Similarly, in an IC chip, I mean the same ideas go whether it is in a PCB or an IC chip or even in a microstrip antenna. Now, if you have done your transmission line course, or even if you haven't, when you get to it, the language will be very different. You will not see wave theory at all. In fact, you will see a distributed RLC network. You will be told that transmission line can be viewed as a two-port network and you can put an equivalent circuit. This distance would be dz this would be C over 2 dz, and this is L dz. And you will be told that this represents the transmission line, an ideal transmission line for a short distance dz. And then you combine many such sections and you get the behavior of a transmission line, which does not look very much like this equation at all. This equation came from studying Maxwell's equations, whereas this is more of a equivalent circuit. So where does this picture fit in with this picture? Well, the way to look at it is as follows. Imagine that we have a parallel plate capacitor which is very long. This direction is Z, and this direction, the direction between the plates, is X, and we do not care too much what is happening in Y. So we have again the possibility of a TEM wave, because we can solve for the capacitance of this arrangement. So we will have electric fields, and then the electric fields will change direction, and that is what is our wave. The wave is going in the Z direction. Now I want to convert from electric and magnetic fields to voltages and currents, because that is what circuits know, and that is what is that equation. The equation has to do with inductors and capacitors. Well, the idea is we have solved for a potential. We looked for E equals minus grad phi. So therefore we can talk about the voltage across these plates. We can calculate integral E dot dl from point 1 to point 2. We can also talk about E dot dl from point 3 to point 4. And let us say that this distance is dz. So in that case, I can talk about the difference between E dot dl from 3 to 4 and E dot dl from 1 to 2. So I can do integral 3 to 4 E dot dl minus integral 1 to 2 E dot dl, which is nothing but loop integral E dot dl, because electric field is up. So these two sections do not do anything. Electric field is orthogonal to dl. What is that? That is nothing but surface integral curl of E dot ds, which is, apply Faraday's law, minus del B del T dot ds. I will pull the del T out. It is minus del T of surface integral B dot ds. But we know that surface integral B dot ds is nothing but flux, and flux is Li. So we can write this as minus del T of Li. Now let us see what we have written. This L, or this flux, is the flux between of a region which is dz wide. So this inductance is L dz, and this difference is voltage at Z plus dz minus voltage at Z, and I am going to take that dz out and bring it this side. Divided by dz is equal to minus del T of Li. This is nothing but the Z derivative of voltage, which gives us a circuit equation. The circuit equation is del V del Z is equal to minus L times del I del t. Similarly, you can get another equation. The other equation will use Ampere's law, and it will give you del I del Z is equal to minus C del V del t. And these two equations together will give you the transmission line equations. The lesson to be learnt here is all the work that we have done in electromagnetic theory, statics, motional EMF, waves, has finally reached here. It allows us to define a wave that is bottled into a pipe. And that wave that is bottled into a pipe, a useful variant of that wave is what we call a TEM wave, and that TEM wave can be modeled by circuit concepts. You can talk about inductance per unit length, and correspondingly you can talk about capacitance per unit length, and you can, instead of talking about electric and magnetic fields, talk about voltages and currents. And when you do that, this is nothing but the theory of transmission lines. And the theory of transmission lines is the practical aspect of electromagnetic theory.